Hello everyone, this is Sumit Sharma and today we will discuss about the IC building blocks. This is the part of your syllabus of paper EL22 Device Models and Circuit Simulation Unit 2nd. So first of all, we should know that what do IC building blocks mean. IC building blocks are the simple blocks or the basic blocks means circuits that are used in the implementation of other bigger circuits in the IC integrated circuits. Like if you consider the op-amp, then it may consist of other small portions, small circuits like active resistor, switches, current sink, source, voltage reference, current mirrors, etc. So we will discuss how we can implement all these small and basic building blocks using BJT and MOSFET. So first in the series we will start from switches. So as you know, you have seen switches in your home, in the laboratory, everywhere there are switches. So the basic use of the switch is to let the current flow between two terminals. Now we will see the switches. So here figure A is showing the basic switch, or you can say the idle switch. It has three terminals, A, B and C. The current will flow between terminals A and B. Look at the cursor. This is the switch. When the switch will on, there will be a direct path between A and B and current will flow. So as normal switches you see these buttons tick tick. In these switches we apply a force who is triggering the switch to be on or off. We are externally applying a force so that the switch will on and it will connect two terminals. Similarly here there is a third terminal named terminal C, which is the control terminal. So we will apply a voltage at terminal C, which will again close the switch between A and B and current will start flowing between these two terminals. So this is the idle switch. Now the figure B shows a non-idle, or you can say a practical switch. So you can compare that many other components like I off, R off, R on, VOS and few capacitors like CA, CAC, CBC and CB are added to this idle switch. See, no idle switch exists, mean ideally there should be no voltage across the switch when it is on, and on resistance of the switch should be 0 and off resistance must be infinity. So these conditions will tell you that in the on condition there is no resistance, so no voltage drop across the terminals A and B, and the total current will flow. Current coming at point A will come out at point B equally. Similarly, there will be no voltage if there is no resistance, no voltage drop, so there is no voltage between A and B in the on condition. And in the off condition, the R off, the off resistance of the switch is infinity, so that there is no possibility of the current to flow between terminals A and B. So what is R on? R on is the on resistance. In the practical switches there will be, it may be very small resistance, but yes, definitely it is there. R on is there. Again, R off represents the resistance, because it is not infinity, it is finite but very large resistance of the order of 10 raised to power 12 ohms. Yes, it is very large resistance but not infinity. Okay, and next is VOS, offset voltage. So what is offset voltage? The offset voltage is the voltage that exists between terminal A and B when switch is on and there is no current flowing between terminals A and B. So it may seem a little bit complicated, that we are saying that switch is on and no current is flowing and there exists a voltage. Whereas we are saying that there in the idle switch there must be no voltage drop across the switch, that is terminal A and B in the on condition, and the current will be there. But here we are saying that the voltage exists between these two terminals A and B when switch is on and no current is flowing. So it seems complicated, but when we will implement this switch using components like BJT and MOSFET, then you will come to know what is offset voltage. Okay. Similarly, IOFF, that is offset current, or the current flowing in the off state of the switch. So ideally there should be no off current because resistance is infinity and there is no current between A and B, but practically it might be leakage current. Okay, so IOFF and VOS, and by definition IOFF is the current between terminals A and B when switch is off but the voltage across the switch terminal is 0. Voltage is 0, switch is off, the current flowing at that time is IOFF. Switch is on, current is 0, the voltage across A and B at that time is offset voltage. We will see it later. Okay. Again there are capacitances, these. So CA and CB are the capacitances between terminal A and ground, terminal B and ground respectively. AC and BC are the capacitances between the terminals A and control terminal, and CBC's capacitance between terminal B and C, and these are parasitic or unwanted capacitances, and the switch on and off time depends upon these capacitance also. We will see it later. Now we will see the ideal characteristics of this controlled switch. Of course it is controlled switch because we are controlling the current between A and B using the third control terminal, that is terminal C. So these are the characteristics. Now you see VA, VB, IA, IB, and there is VC. This graph is between VAB, that is voltage across the switch, and current through the switch, that is IA, or you can say IB. See here, for the switch the current entering must be equal to the current going out the switch. So there exists a voltage VC on, there exists a voltage VC on, after which the switch will be on, and at this point you see VC, at VC on, the current is, that is the current which is plotted at y-axis is here. So at this y-axis, value of VAB, or the value of the term at x-axis, is 0. So you see, in the on condition, or at the condition when VC is such that it is switching on the current between terminal A and B, the current may have any value, but the voltage across the switch is 0. Similarly, there exists a voltage VC off VC off, where the value of current is 0, because on x-axis value of the y term is 0, term in the y-axis is 0. Hence two values are there of control voltage, VC on and VC off. At VC on, current will be there and no voltage across the switch. At VC off, current is 0 and definitely there will be voltage across the switch. So these are the in between values of VC, and VC on is greater than VC3, greater than VC2, greater than VC1, greater than VC off. Okay, so these are the ideal characteristics. Now we will see that how can we implement this switch. The switch we have discussed, what should be its properties. Now we will see that how can we implement this switch using BJT and CMOS. Let's see. So figure here, the first figure is showing the BJT implementation of the switch. So first we will see that how we can implement a switch using BJT. So clearly you can see the base is used as a control terminal. Other terminals, collector is named as A terminal, emitter is named as B terminal. So we will apply a voltage at the base terminal and current will flow from collector to emitter. This is simple BJT action also. Now you see in the last plot, we are interested in the plot between voltage across the switch and current through the switch at different values of control voltage. In the case of BJT, control voltage is the base voltage and the current is the collector current that will flow from collector to emitter. Don't get confused with the naming A, B and C. You can name yourself. It might be base, collector and emitter also. Just we are using A, B, C again so that we can compare this with the ideal switch, because there we have already stated that A, B, C are three terminals. Okay, don't get confused with the terminals. So we have to plot the graph between VAB, that is voltage between the terminals A and B, and IA, that is collector current. So this is the graph. This is the graph here. On the x-axis we have put VCE, collector emitter voltage. Yes, definitely it is collector and emitter voltage, that is voltage across the switch. On the y-axis we have plot IC, collector current, that is in term of switch if we say, that is the IA, the current through terminal A. So you can see the graph shows that the VBE, we have used different values of VBE, like we have earlier used the different values of VC. And what is VC in case of BJT? That is VB, base voltage, base emitter voltage you can say. Now at different values of VBE, the plots are given. You can compare it. You can compare it with the ideal one, this one. Here are the straight lines and there is lot of bending, and even they are not in same proportion in this quadrant and this quadrant. Like you see, this is a straight line, this is a straight line, this is a straight line. But in case of BJT, plot between VCE and IC. In case of BJT implementation of switch, now you see the concept of offset voltage. Earlier I told you that when switch is on and current is 0, so you go for the value of current where IC is equal to 0, then this is 0 value, but voltage across switch at this point is not 0. So there exists a voltage even if current is 0, especially in case of BJT. So this is the offset value. Okay. Next is the implementation of the switch using MOSFET. Source, either, see, the beauty of MOSFET is that these are interchangeable. Which one is at lower potential, that will be source. So A, B, C, three terminals are there: drain, source and gate terminal. We will apply a voltage at gate. The control terminal will be gate. We will apply the voltage at gate terminal, and the current will flow between A and B. Okay, these are the characteristics of a MOSFET. The plot is between VDS, that is the voltage between terminal A and B. So A is drain, B is source. So this voltage is between A and B, and that is between drain and source. Again, the current is ID, the drain current we generally use in the MOSFET. So this is a normal MOSFET plot between ID and VDS at the different values of VGS, and VGS is again the voltage at control terminals. So this is the voltage between control terminal C and terminal B, VGS. So in the MOSFET, you see these lines or these plots are more closer to the ideal one, more straight than BJT, and there is no offset voltage. You see, at ID is equal to 0, VDS is also 0. When there is 0 current, the voltage across the switch is also 0. So from these two characteristics, we can say that MOS can be implemented as a switch better than the BJT switch. So in the next slides, we will discuss about the MOSFET as switch, because we know clearly that MOSFET characteristics are more closer to that of ideal switch. So next is, now we will study this MOSFET as switch in detail. So first of all, we should know that in which region the MOSFET is being operated while it is working as a switch. So you see that we are saying that there should be no voltage or very less voltage across the terminals A and B, or across the switch we can say, and the control terminal should have appropriate voltage so that the current will flow between A and B. So what is this condition? The voltage between A and B, that is VDS, in case of MOSFET should be less, and voltage at control terminal, that is VGS, should be large. This means that VDS is less than VGS, and now you can see this is the operating condition in the ohmic region, where if VGS is greater than VT, the threshold voltage, and VDS is less than VGS, then the MOSFET operates in ohmic region. So we can use the MOSFET as switch in the ohmic region. Now we will see the current, drain current can be defined by this equation in the ohmic region. Earlier also we have discussed this, not in this lecture, but in the previous lectures while modeling the MOSFET and BJT, we have seen that in the ohmic region the drain current can be defined using this equation. Okay, so, and From this equation we can calculate the on resistance of the switch, that is resistance offered by the MOSFET while in the on condition. So we can differentiate this ID with respect to VDS and we can obtain the on resistance. So this is a MOSFET being used as a switch. 4 terminals are there. Bulb can be kept at lowest potential. Okay. These are the characteristics between VDS and ID at different values of VGS over VT. So earlier we have seen the characteristics between VDS and ID at different values of VGS. Again this is similar, but we have now introduced VT, effect of VT in these plots. And again these lines are plotted for very small value of VDS. You see, from here if we keep VDS very small, so these lines will be similar to the straight lines for the idle switch. So to make them more straight, we are using or we are reducing our area of operation, range of operation you can say. Okay. So these lines are obtained when VGS is equal to VT. So when VGS is equal to VT or less than VT, then transistor will not be on and there will be no current between drain and source. So ID is 0. ID here it is 0 at VGS is equal to VT. So as we are increasing VGS over VT, that is VT is fixed for the transistor, we are increasing VGS at the lower values of VDS, and in the ohmic region one can obtain these straight lines for smaller value of VDS. Okay. Now this is the R on resistance, and it depends upon the value of W by L, VGS and VDS. So VGS and VDS we have already discussed that at higher value of VGS current will be large and resistance will be lower. From the equation also we can say if this term is large, definitely R on will be less, and if VDS is small, that is this term will again be large, again decreasing the on resistance. Also we can note the effect of W by L ratio. If we increase the W by L ratio, this value will be decreasing, hence on resistance of the transistor will also be decreasing. So here is the plot showing this effect. This is VGS over VT versus on resistance at these fixed values of K, VT and VDS. Okay. So on resistance is decreasing as we increase the VGS. VGS over VT is VGS only, though it is ratio. The ratio is just to show you that when VGS over VT is equal to 1, this means VGS is equal to VT. When VGS over VT is less than 1, this means VGS is less than VT. So below the value of 1, there is infinite resistance between drain and source, or you can say the terminals A and B of the switch. Okay. So the current will start flowing only when VGS is greater than VT or when VGS over VT is greater than 1. Now we will see the effect of W by L ratio. So as we are increasing the W by L ratio, increasing W by L means we are increasing the width. Okay. So as we are increasing the width of the channel, the resistance value is decreasing. Okay. So resistance can be decreased using W by L and VGS, keeping VDS low. The reason for keeping VDS low is also that we want the MOSFET to be operated in the ohmic region only. I think now it is clear to you. So again, the next term that is associated with the switch is the voltage levels of the terminals. So this is very important issue. What can be the voltage levels at the terminals? So here in this figure, a switch is applied between these two circuits. Definitely this is the use of the switch, that it will be connecting these two circuits. So current will come from this circuit and it will flow through the MOSFET and it will reach the circuit 2. These are the typical values of the voltages that can be applied to a circuit. Now see, source and drain you can interchange. For the N MOSFET, which is at lower potential, that will be the source. Now -5 is the negative value of the voltage, +5 is the positive value. So +5 will switch on the transistor or switch on the switch, and -5 will make it in the off condition. Now you can understand the problem. Up to what value this terminal can achieve the voltage. Okay. Take an example that Vt is 2 volt. The threshold voltage is 2 volt. So now think up to what value the transistor will be on. The MOSFET transistor is in on condition when VGS is greater than VT, and it will be in ohmic region when VDS is less than VGS minus VT. Okay, so we take the control terminal voltage or the gate voltage, we can say 5 volt. The purpose of this switch should be that it will connect this circuit 1 to circuit 2, or it should raise the voltage at this point from -5 to +5. Okay, yes, this is the purpose of the switch. It can raise the voltage, or it should equate, it should make the voltages at two terminals equal. This is the function of switch. Now suppose threshold voltage for this circuit is 2 volt. VDD applied is VDD, or you can say VGS also is 5 volt. When switch is on, this terminal or this terminal, either terminal, suppose this is at 5 volt, this is at, so let us clarify this. So this is termed as drain, so it is at higher potential. Suppose this is at 5 volt and this is source, so this will be at, initially it is at lower potential, -5 volt. Okay, so function of the switch should be like that. When we on the switch, when we switch on the switch, so it should make the voltage at these 2 points equal. So if it is at 5 + 5, it will be also at +5. So the purpose of the switch will be solved. Now Vt is 2 volt, VDD, this voltage is VDD at circuit 2 is 5 volt. When switch is on, it will start increasing this value from -5 to +5. It will go from -5 to +5. When it reaches +3 volt, what will happen? We have applied 5 volt at gate, source has been reached at +3 volt. So what is gate source voltage at this point? This is VGS is equal to VG minus VS, that is the difference between gate voltage and source voltage. Source is now at 3 volt because this switch is on, and now it is forcing this terminal to be equal to this terminal. So in this process it has reached up to 3 volt. After reaching at 3 volt, what is the value of VGS? That is 5 minus 3 equal to 2 volt. It means VGS has become equal to VT, and we have seen if VGS is equal to VT or less than VT, the transistor will not on. So automatically the transistor will go into the off condition. Okay, so this is the point we should consider, that what will be the voltages at the terminals. So it cannot make it up to the 5 volt. The reason is before you, because at that point where VGS will be equal to VT or less than VT, the transistor will go off. Okay, now this is the circuit where a switch is used to charge a capacitor. The capacitor C is to be charged through this switch using this potential V in. So phi 1 is clock, or you can say this is the voltage we will be applying at MOSFET M1. So when this transistor is on, V in will be connected, it will be shorted. V in will be connected to the capacitor and it will be charged. So this is the equivalent circuit of this. In the on condition, practically there is resistance, that is R on. So MOSFET is replaced with its own resistance R on. Current will flow through this R on and capacitor will be charged. So there is time constant, which is RC, R on into C1. So this will be the time taken to charge the capacitor C1. Now you see, this RC time constant should be very less than the time period of this clock. It means the capacitor must be charged before this switch goes off. And from this figure we see that when it will be go off. Normally it is a clock, and clock will be used to switch it on and off. So the time period of the clock should be such that it is sufficient to charge the capacitor. Okay. Next is the practical switch. Here we have added the capacitances, these capacitances GD, GS. In the ideal switch, from where we started the discussion, a figure below that was given in which a non-ideal switch was shown and some capacitors were added to that. And at that time we discussed that they are unwanted capacitances, they should not be there, and charging and discharging of the circuit, or we can say switching on and off the circuit, depends upon those capacitances. So here is the practical circuit, that how actual a MOSFET can work as a switch. Just we have taken this arrangement, we have added the capacitances associated with the MOSFET device to this circuit, and this is redrawn here. You can see gate, drain, source, 3 terminals are there. Capacitances are between drain and gate, source and gate, source and bulb, gate and drain and bulb. These are the capacitances. And here this is the phi 1 clock. Next concept to be discussed is the clock feed through. This is very important, the clock feed through. Our purpose is to switch on this MOSFET device. It will give a path for V in to charge the capacitor. Okay, so we want that only V in should charge the capacitor, and while charging there should be no role of phi 1 to charge C1. Only V in should charge C1, the capacitor. Role of phi 1 is to just make a path to connect this circuit. Otherwise it should not have any other purpose. But when we apply a clock here, these capacitances, see, these capacitances are connecting this clock to the capacitor. So they have a role, unwanted role definitely, but yes, there is role of phi 1 to charge or discharge the C1. We will see it. First we see, this is the waveform of the clock applied to the phi 1. So though there is not much slope, but for our understanding it is shown here. So we will discuss the different levels. This is VT, the threshold voltage level, V in, this voltage level, V in plus 1 VT here, and clock applied is of 15 volt maximum. T0 to T1, time taken to reach up to the VT, T1 to T2 to reach up to full value of the clock, then T2 to T3, it will be on when the switch will be on, T4 to T3 to T4, that is from full value, that is 15 volt down to V in plus VT, then T4 to T5. Now we will discuss this whole waveform with this model. So when VGS, definitely phi 1 is VGS, or the control voltage or the gate voltage, anything you can say. So below that there will be no current because it has not reached VT. Okay, when it will be crossing the VT, the switch starts turning on and it is on. Now you see, when switch is on, so before VT, this capacitor comes into action, this, okay, but it is not connected to C1, so we will not consider it. When switch is on, this capacitor should be come into action. So when switch is on, this V1 is connected to the C1, V in is connected to the C1, and it will start charging the capacitor. So up to now there is no problem. The problem will start when this phi 1 or the switch starts turning off. So this is the level at T, from T3 to T4 it will start turning off. And can you say that when the switch will be off? It will be the point from at T4, this point, V in plus VT. V in is drain. One thing I would like to mention here, this is named as source because we thought that the capacitor was discharged earlier, so this was the lower potential, so we consider it as source, and it was connected to the V in potential, so it was considered as drain. Okay, so when the voltage at gate or the control voltage reaches V in plus VT, the switch will turn off. Can you tell why? We have seen this effect here, like the transistor was switched off when this level reached, VGS reached control voltage minus VT. Okay. Similarly here, when it will become V in plus VT, so this is V in plus VT, the transistor will be in the off condition. Is there any doubt that why it will be off? So let me clarify it. V in is disconnected. Now the voltage at terminal VGS is this voltage minus this voltage. Voltage at source is V in. If we say that the capacitor is charged up to V in, because V in is the voltage charging the capacitor, so VC1 is equal to, say, V in it is. Okay, if the capacitor is fully charged, it will be equal to V in. Now the voltage at gate source terminal is, what is the voltage? VG minus VS. VG is here, VG have reached here, V in plus VT, and voltage at source is V in. So difference of voltages is V in plus VT minus V in, that is VT. Again the effective voltage or the gate source voltage have reached VT. So when VGS is equal to or less than VT, the transistor will be in off condition. So now you see, this capacitor is now coming into the action. It is feeding the capacitor, or it is giving a path to the capacitor to discharge. Now you see this path. This is disconnected now. This is off. So it has nothing to do with this circuit. Now it is disconnected from here. Switch is off. So the capacitor may discharge due to the presence of CGS. It will be very less value. The loss of voltage by capacitor through CGS will be very less, but it is some value. So we can calculate this value using this equation. Delta VC1 is the change in the capacitance when feed through action is taking place. So this capacitor is feeding through this capacitor, or it is discharging this capacitor through this path. You see. Okay. How much it can discharge this capacitor? That is this one, CGS over C1 plus CGS into V in plus VT, because we are considering this point. So this voltage, this combination of the capacitance, and if we take the normal values, and they are, the C1 can be 1 picofarad, CGS can be in the range of femtofarads, and we take it like 2 femtofarads, say. V in we know is 5 volt, VT you can take 2 volts. So this will come 0.002 V in. So by this value, this voltage will be decreasing. So if V in is 5 volt, then there will be change of 10 millivolts, or you can say, due to the feed through effect, due to the discharge of this capacitor through this CGS capacitor, the voltage at capacitor has been decreased by the amount of 0.002 V in. That is, for V in is equal to 5 volt, it will be 10 millivolts. It seems very less value, but in some circuits it will be of great importance. Okay, we will stop the discussion here. You can contact me if you have any doubts. Thank you.